Hi, welcome to this video. Now we're gonna have a sample problem regarding the convection heat transfer. Okay, so determine the rate of heat loss from a solar collector panel array attached to a roof and exposed to an air velocity of 0.5 meter per second. The array is 2.5 meter by 2.5 meter square. The surface collectors is at 70 degrees Celsius and the ambient air temperature is 20 degrees Celsius. Okay, so based from the problem, we need to determine what? Okay, so let's analyze this problem based on the given problem and what is being asked. Okay, so we asked to determine the rate of heat loss. So we need to find the Q, right? Rate of heat loss. Okay. Okay. So our condition is that we have a solar collector panel array attached to a roof. So let's have some illustration so that we can easily visualize the problem and analyze the problem easily. Okay, so we have a solar collector. Say this is your building. Say this is your building, and you have a solar collector that is attached to the roof of the building. Say this is a solar collector. Okay, so say this is your solar collector array. Okay, so this collector is exposed to an air velocity of 0.5 meter per second. Let's say the air is from here, air velocity of 0.5 meter per second, and then the array is, so it is the dimension of the array, 2.5 meter by 2.5 meter. This is 2.5 and this is also 2.5. Okay, what else? The surface collector is at 70 degrees Celsius. So this surface is 70 degrees Celsius, right? And the ambient air temperature is 20 degrees Celsius. So our air is at 20 degrees Celsius. Okay. So let us determine the rate of heat loss from the solar collector. If we have the air that is flowing through this 2.5 by 2.5 solar panel array with 70 degrees Celsius. So if we're gonna draw the heat loss, then from the higher temperature surface, you can have a heat loss Q, right? So let us determine the heat loss from this solar collector array. Okay, so for the solution, since we have this information and we know that we need to determine is the Q, then let us say that our Q loss, or Q dot, whichever the symbol you're gonna use. For me, okay, let me change it. So we have a common symbol. Okay, let me use this symbol Q dot instead for heat loss. So Q dot is equal to, what is our formula once again? So go back to our basic formula that Q is equal to H A temperature of the surface minus temperature of your fluid. Okay. So we don't know the H or the coefficient, convection coefficient, heat transfer coefficient. The area is given by this dimension, so we have 2.5 meter by 2.5 meter, and then the temperature of our surface is 70 minus fluid is 20 degrees Celsius, right? Okay. So we have this equation. Let's call it equation 1. Okay. So from equation 1, we notice that in order for us to determine the heat loss, we need to find the value of our H. And like what I am saying, that the main challenge here really in convection heat transfer is to find the value of our heat transfer coefficient, because different conditions of your setting will affect the value of this H. So based from our given, let us determine the value of our H. So how can we determine this? Okay, recall from our discussions last time, we have the different different dimensionless numbers, right? Okay, so what are those? The Nusselt number, the Reynolds number, the Prandtl number, the Grasov, the what else? Rayleigh, and so on, right? So based from those dimensionless number, we also discussed where those numbers can be applied, okay? And since this condition is what? So based from this problem, we have a flat surface, right? So we are dealing with this panel. So we have a flat surface, and we already have discussed some important matters regarding this flat surface. Okay. So as we recall, one of those important things is regarding the Nusselt number, right? Because from Nusselt number, as you noticed from the equation, we have H, characteristic length, divided by the the specific what do you call this letter K? The thermal conductivity. Okay, so based from here, to determine the Nusselt number, we need to know the H once again, but we don't know that yet. The LC, or the characteristic length, and the K. Okay, so the LC is given by this. Say the air is flowing through this, so our characteristic length is this one. So we have a 2.5 meter characteristic length, right? So therefore, H is equal to 2.5 meter divided by K. Okay. So as you noticed, we cannot still compute the value of the Nusselt number. Okay. But if you can also recall, we have some terms and working equations that we can relate this Nusselt number depending on the conditions, right? So if you can still remember, I have also presented a table with the flow regime having a laminar and turbulent flow with a heat transfer coefficient depending on the condition, if you want a local or the average one. Oops, sorry. Same goes with the turbulent flow. We can have the local and the average H and its correlation and the given condition. Okay, so what's the correlation once again? That the Nusselt number is equal to 0.332 RE 1/2 Prandtl number 1/3. Okay, and NU average is equal to 0.664 RE 1/2 PR 1/3. So their condition is that the PR number is greater than or equal to 0.6. Okay, so for the turbulent, we have the local correlation of NUX is equal to 0.0296 REX 4/5 PR 1/3. NU average is equal to 0.037 RE 4/5 PR 1/3. Okay, so that is for the condition 0.6 less than or equal to PR less than or equal to 60. So ranging from 0.6 to 60. Okay, so if you have a different condition, you need to search for a different datas or equations. Okay, so this only applies to this PR conditions. Okay, you can use this for only these conditions. Okay, so going back, since we have NU and we have this correlation, but as you can see here, based from these correlations, the NU can be equated to these numbers, but we need the values of our RE and PR, right? So that is true for all these conditions or correlations. So how can we determine those values? Okay, so let me search first for these conditions. Okay, so to determine the flow, we need to know the RE or the Reynolds number. Okay, but before that, if you can also still remember, we have also tackled the what we called the what do you call this? The film surface temperature. Right? So the film surface temperature is the average of your temperature of the surface and fluid. So we will only divide it to 2. And the temperature of the surface is 70 and our fluid, which is air, is 20. So we have 70 plus 20 divided by 2. So our film temperature is about 45 degrees Celsius, right?